Okay. If we look back to the hybrid motor operation that we've seen just now, think about here. Oops. Try to silence this one. Okay, so when we look at how this hybrid motor operates, we see that the step angle progress actually or the rotor actually rotates based on the step angle progress when we have the change of polarity here. For example, when there is a change of polarity, the rotor itself will try to align so that the magnetic poles of our opposite side attracts and poles with the same type propels. So we can see what happens here, that when you have changes to red, then the rotor itself move so that the red side of the rotor will be away from the right side of this stator. Okay, right. So before we move forward, I would probably want to clarify things that were not quite clear with this video, which is on driving a stepper motor. I think this video has a better explanation on this. Just let me turn on the sharing first. Okay, so let's see on driving parts. Okay, all right, so let's straight away go
full step, half step, and micro stepping. By these modes, you determine the performance and torque of the stepper. The full step mode provides high torque because all coils are always energized. The rotor needs 4 steps to complete a 360-degree rotation. However, you have full and constant torque at all these steps. However, this mode does not improve the resolution.
We can see from here that the movement from when the poles are changing makes the rotor move like 90 degrees at a time, which means the resolution will be very bad, and we can actually see the rotation is actually quite jittery. But these kind of types of operation, okay, actually have the highest torque possible, because the poles are excited one at a time, and we can see that the movement is actually quite large. Okay, but the step angle is 90 degrees.
In half step mode, you get a step angle half of the angle in full mode, so the resolution already doubled. On the other hand, you get no constant torque.
Okay, so in half step, in comparison to the full step that you've seen just now, is that we can see that there are 2 poles that are activated at a time, and we can actually increase our resolution twofold, in which if usually we have 90 degrees, then we will have a 45-degree step angle. Okay, so this depends on number of poles on the machines, but the torque in this case is not constant. Okay, mainly because the torque in this type of operation, okay, because of the changes between these poles during the half stepping mode, reduces or basically varies the amount of magnetic field inside the machine, so therefore the torque is not as constant as we've seen in the full step mode.
However, micro-stepping is the most common method of controlling stepper motors nowadays. Here, the coils are provided with a voltage similar to the form of sine wave. As a result, you get smooth motion of the rotor, less stress to the parts, and the accuracy of the stepper motor increases significantly. Unfortunately, in microstepping, the torque is decreased about 30%.
Okay, so we can see now in micro-stepping mode, we actually give or activate each of the poles with different amount of voltage. And this different amount of voltage is activated during this what we call or the on time for each of the voltage follows sinusoidal wave. Okay, so when we follows this, the movement is quite smooth. Okay, the movement is smoother in this case, but we will decrease the torque to about 30% because the changes are more frequent. We can't really hold the torque, or we don't have what we call a large holding torque at each position. So therefore, during this micro-stepping, because changes are quite fast, we actually lose also the amount of torque.
For the user, the torque speed curve.
Okay, so this is actually what happens when we drive the stepper motors. Okay, before we go further to this operational torque speed curve of a stepper motor, I would like to bring your attention to what we call windings on a stepper motor. If you buy a stepper motor, you will see that there are two actually types of stepper motor, which what we call unipolar stepper motor and bipolar stepper motor. So for example, in unipolar stepper motor, there are, in this case, three types: the 6-lead, 5-lead, and 8-lead connectors. In each of these, you'll see that there is a center tap. What we call it center tap here. Okay, so in unipolar winding, there is two coils. We can see that there is two coils here. This red and black, red to black, and then red and white to black. So there are two coils per pole instead of only one. So unipolar means that the current in the winding always flows in the same direction. So typically the center tap is where we connect the positive voltage, and if you want the current to flow the like from black to red, then we actually ground the red. And if you want to current to flow from black to red or white here, then we will connect the ground to this red and white connection. Okay, so in this case, we see that for operation of unipolar stepper motor, we will have one of the winding activated at a time, and to determine one direction. So basically, in these two coils, you can actually activate one type of coil to rotate a motor, for example, clockwise, and another type of coil to rotate the motor counterclockwise. Okay, so unipolar here means that the current in the winding always flows in the same direction. Okay, so either black to red, or black to red and white, or white to green, or white to green and white. Okay, so the advantage of actually using the unipolar winding is that we will have less transistors in comparison to bipolar stepper motor, in which we have to change the direction of a current because the coil is only one. And the transient response to changes of steps are faster. Okay, so in the bipolar winding or bipolar stepper motor, for example, it has one coil per pole. So you can see here red, yellow, and black, orange. So the for the motor to rotate clockwise or counterclockwise or change direction, the current in this coil will have to reverse periodically, and they must be excited by kind of like a bridge, okay, so that the current can actually change direction. So these coils typically can be excited through three different ways, what we call a wave drive, or normal drive, or half step drive. So in the wave drive, only one set of coil is excited at a time, and you will have switching sequence like this full step that we've seen before. In normal drive, you will have both set of coils are excited at a time, and you have a switching sequence. In a case that the rotor itself will point to, for example, northeast, southwest, or southeast and northwest. So instead of going, you know, north, south, east, and west. Okay, so it will go like in position where it's not, or it's in 45 degrees direction in comparison to, you know, a typical 0, 90, 180, and 270 degrees direction. Okay, and the other one is using what we call a half-step drive, which is combining both a wave drive and normal drive, or full drive and normal drive, and the flux actually now will rotate 45 degrees per step. So in any case of this excitation of coils, this type of winding will need different drivers for that to operate. And we can see that unipolar stepper motor will only need a driver that can actually activate them, you know, just simply one directional current. But for a bipolar, you need a two-directional current, which is current should be able to switch direction. So if power arrangement, like I said, for unipolar and bipolar is different, and you can see that in case of unipolar, you have a center tap connected to a positive voltage, and you know, one side of coil to be grounded if you want the current to flow in this direction, or the three ones or the third ones can be grounded if you want the current to flow the other way. Okay, so the current flow actually determine the rotation of the rotor. For bipolar, you will have a separate connection for each of the winding, and you can see that the driver should be able to reverse the amount, the current, okay, flow. So the good thing is that we can see for a bipolar case, the coils that we see here are fully responsible for the amount of magnetic field strength that we have in the machine. But in the case of unipolar, at any point of the time, only half of this coil, or basically one of the coil, because you have two coils, so one of the coil is activated at one time. So for example, if you are rotating in counterclockwise, so say only 1 and 2 are grounded, so that it rotates in this in counterclockwise. Okay, so and if you want to rotate in the other direction, then only 3 and 4 are connected. Okay,